Welcome back to Math 104. Earlier today we actually were looking at our Unit 2 guided notes. We started by simplifying rational expressions. We then moved into multiplying and dividing rational expressions, and we started to talk about what it looked like when we added and subtracted rational expressions with common denominators. We actually left off on one last problem that I was hoping you all would try at home, especially right after class and some material was fresh. So we're going to cover that first before moving into what happens when we don't have a common denominator and how to go about fixing that. Okay, so let's take a look. I'm so happy that you can join me today. Let's check it out. So here we have 3m over m plus 4 minus 4m squared plus 20m plus 4 all over m plus 4. Notice here we're definitely subtracting these two fractions or two rational expressions. Also notice that I have a common denominator, m plus 4. The one thing that we really wanted to harp on was the fact that because we are subtracting these expressions, we want to be sure to distribute our negative sign throughout this second fraction, throughout the numerator of this second fraction. So what we learned earlier today is that essentially, let me just turn this for a moment, essentially we're going to rewrite the numerator by distributing that negative sign. So we have 3m minus 4m squared minus 20m minus 4. Notice that we have a common denominator, so we're simply going to write m plus 4 in our denominator. The other thing I like doing too in this case is I actually like putting parentheses around my expression in the denominator because this is essentially my factored form, right? What we learned is that we always try to combine the numerators and then factor everything and see if there's any way that we could divide out common factors. So with that in mind, I like to put parentheses around that denominator since it's simplified completely, meaning it's in its factored form. There's nothing else we really could do with that denominator. But check out the numerator here. So when we go ahead and combine like terms, notice that we have a negative 4m squared as my leading term. I then have 3m minus 20m. That's going to give me minus 17m. And then, of course, we have minus 4. All of this is written over m plus 4. We're definitely far from finished with this particular problem. The next thing we're going to want to do is we want to factor out our leading negative. We learned that anytime we have an expression that our leading term has a negative number, we want to factor that out. So factoring out that negative 1 leaves us with 4m squared plus 17m plus 4. At this point, we're ready to take a look at that trinomial and factor if possible. Luckily for us, we find that when we factor our numerator, 4m squared plus 17m plus 4, we actually are left with 4m plus 1 times m plus 4. Notice here, 4m squared plus 16m plus 1m, that gives us our 17m plus 4. There's our 4. We also discussed in class that if you wanted to verify that this was correct, that you would come back to this problem and kind of test it out. I will let you know as a reminder, you will be using AC grouping to factor this particular trinomial. Let's go ahead and write this expression over m plus 4, which was our common denominator. And then lastly, we can say, hey, let's reduce, right? We're going to divide out our common factor of m plus 4. So our final answer is going to be negative 1 times 4m plus 1. You can and should leave your answer in this factored form, okay? And that concludes adding and subtracting rational expressions that have the same denominator. Now let's take a look at what happens when they're different. Let's recall our experiences in the past with adding and subtracting fractions that don't have the same denominator, right? So for instance, notice here we have 7 over 15 plus 6 over 5. What we learned a long time ago is that when we were looking for the least common denominator, That's essentially the same as locating the lowest common multiple, right? So when we think of multiples, we think of taking that number and multiplying it by integers. So for instance, positive integers. 15 times 1 is 15. 15 times 2 is 30. 15 times 3 is 45. And we can essentially keep going and going and going. So those are my multiples of 15. My multiples of 5 are 5, 10, 15, 20, etc. Now, because I'm looking for a common denominator, I want to look for a number that both of these denominators can become. Another way of thinking about this is, how can I make them the same, right? What factor can I introduce that would make them the same? By listing out the multiples of each of my denominators, I can say, well, they both have a common 15, right? Remember, we're not dividing our denominator to find a smaller one. No. We are looking for a common denominator by introducing a factor that will make them match each other. So for instance, I notice that my LCD in this case is going to be 15. So to make this happen, I recognize that I have to multiply my 5 by 3. What you do to the denominator, you're going to do to the numerator. As a reminder, we are allowed to multiply this one fraction by 3 over 3 because that is the same, hi Jeff, that is the same as multiplying by 1. 6/5 times 1 is still 6/5, right? So even though that 1 looks different, it looks special, it's 3 over 3, it's the exact same value. So then this becomes 7 over 15 plus 18 over 15. And of course, now we can actually combine these. So that's what gives me 25 over 15. And then you would always say, well, I'm never going to leave my answer like this because I know I can simplify it. You know that you can divide each numerator and denominator by 5. And that's what's going to leave us with the answer 5/3. So there's my final fraction. I want you to keep all of this in mind as you move through more complex problems. Let's take a look at B here. We have 7 over 10 minus 8 over 15, same thing. Think about a number they can both become. When we think about this logically, 10, 20, 30, 15, 30, I'm recognizing that these denominators have a common multiple of 30. So in order to make that happen, I would multiply the first fraction by 3, right? Because 3 times 10 is 30. What you do to the denominator, you must do to the numerator. And then with my second fraction, I'm going to multiply by 2, because 15 times 2 is 30, and what you do to the denominator, you do to the numerator. This is going to leave me with 21 over 10 minus 16 over 10, and in which case this be, oops, did I write 10? Wow, that's, sheesh. This is what happens when I think too quickly. So 21 over 30, yep, I fixed it, minus 16 over 30, and then of course, combine these two. When you combine these two, you get 5 over 30. As always, you're not going to leave your fraction in this form. You're always going to reduce. We'll divide both by a 5 for a final answer of 1/6. Okay? Lastly, same exact idea here. Notice your denominators are 4 and 5. They can both become a 20. So we'll multiply the first fraction by 5 and the second fraction by 4. It's kind of neat that essentially what you ended up doing here was multiplying each of them by the other denominator. That can always work. It actually does always work. Sometimes that might not give you your lowest common denominator, but it will be a common denominator. So if you're ever feeling stuck, you can definitely use that strategy. So here we have 5 over 20 plus 12 over 20, and that's what gives us 17 over 20. And of course, we can't simplify that, so we'll leave it as is. Finished. Okay, let's turn the page and get into some good stuff. Okay. We talked about LCD versus GCF. I'll let you look at this and kind of dissect that on your own. Let's actually get into it. So we want to find the lowest common denominator of a rational expression. I think the big piece here that has always helped me as I was learning is thinking about it in terms of what's missing. What factor can I introduce so that they end up being the same, right? What factors can I introduce so that they end up being the same? You want to essentially build these denominators so that they become identical. That's what you're looking for. So when you're strategizing, think, what should I multiply by so that they can be identical? Sometimes you only have to multiply one fraction, sometimes you have to multiply both, right? It doesn't matter as long as you're focused on how do I make them the same and identical. So I'm going to try to talk through this in a more informal way so that you kind of get a sense of what you're looking for and how that strategy works. Okay, let's check it out. So for part A, I have 5 over 36x squared y squared minus 35 over 12xy squared. Now I want you to notice here, the only thing I'm doing initially is I'm simply finding the least common denominator. That's all I want to do. I'm not using it yet. I just want to figure out what the heck is the LCD. So I'm going to write out LCD equals. The first thing I look at is the 36 and the 12. If we have a 36 and a 12, we have to think about how I can make them the same. My mind automatically goes into, well, I know that if I take this 12 and I multiply it by 3, I get 36, right? So we're recognizing that both denominators can become a 36. So far, so good. And what may be helpful is you write down what you have to multiply by to make this happen. So I'm just going to jot down that I have to multiply so far by a 3. Next, let's compare the x's. Notice I have 2 factors of x in my first denominator, but only 1 factor of x in my second denominator. If I introduce another x, then suddenly my second denominator also has an x squared. So x squared is looking great. Lastly, both of my denominators have y squared, which means my LCD is simply 36x squared y squared. Just to prove a point, because we determined what factor was missing so that we can get them to be identical, I want to show you what this looks like if I were to multiply the numerator and denominator by 3x. First off, the first fraction does not need to change. It already had the denominator we were looking for, so that one stays exactly as is. For my second fraction, I needed to multiply by a 3x. What you do to the denominator, you must do to the numerator. So this means we have 35 times 3, and if we take 35 times 3, we're going to get 105. So 35 times 3x is 105x, and then over, and when we multiply our denominators, we get 36x squared y squared. So we can confidently say, okay, I was successful. I introduced the factor 3x so that I can have the same exact denominator. You can play around with this idea until they're identical, okay? Taking a look at part B, it's actually a lot nicer than part A. It's much more simple. We have 4 over x minus 2y over 5x. Immediately when I see something like this, I think, well, they would be the same if my first denominator had a 5, right? If my first denominator had a 5 in front, they'd be identical. So simply put, if I were to multiply by 5, I then have 20 over 5x minus 2y over 5x. Success! I found out that my LCD had to be 5x. Now remember, we would take this a step further, but right now we're just focused on finding the LCD. Okay, we're not simplifying. We're just trying to figure out what the heck is the LCD in the first place. Good. Look at part C. Your first fraction has a denominator x plus 5 times x minus 5. Your second fraction has a denominator x minus 5. Do you see what's missing? In order to make the denominators the same, the only thing that's missing is that this second fraction needs an x plus 5. So if I introduce this x plus 5 in the second fraction, I now have the common denominator. So just so you know how to rewrite this, we have 3x over x plus 5 times x minus 5 minus x plus 3 times x plus 5 all over x plus 5 times x minus 5. So we have just discovered that our LCD is x plus 5 times x minus 5. That's what it would look like. Of course, to progress, we would want to distribute just the numerator so that I can then distribute the negative throughout and combine my numerators and make one fraction. But we will see that in just a little bit. Take a look at part D. We have 3x over x plus 4 minus 1 over x times x plus 4. Look at the denominators carefully. You see what's missing, don't you? All we're missing is the x, which means we need to introduce a factor of x in the first fraction. So we're going to multiply by x here, and we're going to multiply by x here. X times 3x is 3x squared, and we have our denominator as x times x plus 4. Then we have minus 1 over x times x plus 4, and again, we have determined that our LCD is x times x plus 4. Okay, excellent work here so far. Part E is a little bit interesting because we actually already learned, for instance, that 4n minus 1 divided by 1 minus 4n leaves us with a negative 1. So these two expressions are incredibly similar. What we may want to consider is that if I want to find the LCD, I really want to look at these in terms of descending order, right? So the first thing I'm going to do here is I'm going to note that I have n over 4n minus 1 minus, and then I have n plus 8. My denominator in this case is negative 4n plus 1. Whenever my leading term is negative, I want to factor that out. So now I have 4n minus 1 in my first denominator, and I have negative 1 times 4n minus 1. The beauty about factoring that negative 1 is that we can then influence the negative sign connecting the two fractions. Recall that when we have a negative fraction, so for instance, if I had 4 over negative 7, that is the same as writing negative 4 over 7. We can bring that negative to the front. So having said that, we recognize that a negative divided by a negative becomes a positive. So my expression becomes n over 4n minus 1 plus n plus 8 over 4n minus 1. Our denominators are the same, so we won't have to multiply by anything. We don't have to introduce a missing factor because my LCD is 4n minus 1. All we had to do was manipulate what we were given so that it's in descending order. We factor out that leading negative, and then of course we clean up our signs. Always clean up our signs. Good, let's turn the page and keep looking at some more problems. So for part F, we have 2 over 12x to the third plus 4 over 9x. So I'm looking at that 12 and that 9 first, and I'm thinking to myself, well, okay, multiples of 12 are 12, 24, 36, boom, and I'm going to stop right there because I know that 9 can become a 36. So let's think about this. I'm starting to build my LCD. I'm saying I know that the 12 and the 9 should become a 36, which means for my first fraction, I'll be multiplying by a 3 so far. And for my second fraction, I know so far I'll be multiplying by a 4. Then I take a look at my variables. I have x to the third and x to the first. Well, I can easily make these the same by multiplying my second fraction by 2 more x's. So that means my LCD is going to be 36 x to the third. Let's verify that. It's always helpful to kind of see the math in action so that we can verify that we're doing the correct thing. 3 times 2 is 6. 3 times 12x to the third is 36x to the third plus 4 times 4x squared is 16x squared. 9x times 4x squared is 36x to the third. Success. We have the same denominator. So every time that's what you're looking for. What factor can I introduce to make them the same? For our next one, we have 12 and 16. I would start with the 16 and I would say, okay, well, 16, then our next multiple is 32, and then after that it's 48. Here we have 12, 24, 36, 48. So we're finding that our LCD has to have a 48. So to make that happen, I'd be multiplying the first fraction by 4, maybe a little bit more than that, and I'd multiply the second fraction by 3. So far, so good. Next, I have 3 x's in my first denominator, but only 2 in my second. So in order to make them the same, I've got to introduce 1 more x here. This way, I get x to the third. And then I have y to the fourth in my first fraction, but only y squared in my second. So if I introduce 2 more y's, I then have y to the fourth. As always, let's verify that we get the exact same denominator in each case. 4 times 7, that's 28, over 4 times 12x to the third y to the fourth is 48x to the third y to the fourth. Then we have minus 11 times 3xy squared is 33xy squared all over 48x to the third y to the fourth. 48x to the third y to the fourth. Success. Check out the next one. This one's pretty interesting. There are a couple ways to go about this. One way is to actually open these up just so you can see what's happening. The only thing with that is it can get really messy quick. So instead, we want to be cognizant of those powers as we examine our factors. So let's look at these carefully. My first fraction has 2 factors of x minus 2, while my second fraction only has 1. If I introduce 1 more, then that means I've achieved that x minus 2 quantity squared that I have in my first fraction, right? But then notice that my second fraction has an x plus 3 to the third power. So what that means is we need to introduce that x plus 3 to the third power to our first fraction. So essentially, we would end up with something that looks like that. So we find that our LCD is x minus 2 squared times x plus 3 quantity cubed. Now I will tell you that in this particular class, I wouldn't ask you to do a problem like this. It's kind of messy. You'd have to open up x plus 3 3 times. You'd have to distribute, then multiply by x, etc., etc. Notice here that my denominators are in fact the same. X plus 3 to the third times x minus 2 squared. X plus 3 to the third times x minus 2 squared, because there's 2 factors here. Perfect. Take a look at part I. We have x plus 1, x plus 4. In my second fraction, I have x plus 4, x plus 5. Just think about what's missing. They both have an x plus 4, which is cool. This first fraction has an x plus 1, which means the second fraction needs the x plus 1. The second fraction has an x plus 5, which means the first fraction needs that x plus 5. And we have just found the LCD. X plus 5, x plus 1, x plus 4. The product of all three. Crazy, right? That's why I like identifying this as saying what's missing. Just introduce the factor that's missing so that they become the same. I'm hopeful that as we're seeing these problems that it's starting to be very clear that if you're seeing a factor that's in one fraction that's not in the other, that you're going to introduce that into the one where it's missing, okay? So don't overthink that you're just kind of, putting those puzzle pieces together. Take a look at part J, though. This is slightly different. For part J, we have 3 over 4x squared minus 12x plus 2x squared over x squared minus 6x plus 9. The reason that this one is different is because your denominators have not been factored yet. We need to start there. So I'm going to rewrite this. We have 3 over. Now, with 4x squared minus 12x, we learned that the very first step of factoring is always GCF. GCF. Yes, I did chant that. So we're going to factor out a 4x. If I factor out my 4x from each of these terms, I'm going to be left with x minus 3. So now my first denominator is completely factored. Plus, now I have 2x squared all over. And notice here we have x squared minus 6x plus 9. Since this is a trinomial where my leading coefficient is 1, I'm going to use trial and error, which means I need to find factors of positive 9 such that when I combine them, I get a negative 6. Well, 3 times 3 gives me 9. A negative 3 times a negative 3 also gives me a 9. And a negative 3 plus a negative 3 gives me a negative 6. So it's going to be x minus 3 times x minus 3. Perfect. Now that your denominators are factored, we can then say, all right, what are we missing? First things first, I notice that I have a 4x in the first fraction, but I don't have one in the second. So I'm missing a 4x. The next thing I notice is that I have an x minus 3, but my second fraction has 2 of them. So I need to introduce one more. What you do to the denominator, you do to the numerator. This implies that our LCD is going to be 4x times x minus 3 times x minus 3. Now, if we wanted to, we can definitely write that as the square of a binomial. So we could write it as, or 4x times x minus 3 squared. That would also be acceptable as a way for you to write your common denominator, okay? Either or is totally fine. I like opening it up so that you can see the factors, and you could just double check to make sure that both denominators have exactly the same factor. For part K, things get a little bit tricky here unless you remember that anytime you have an expression in your denominator, like something like x plus 5, you should keep it in parentheses so that you can look at it as a package deal. So having said that, when we have 4 over x minus 2y over x plus 5, I immediately recognize that this first fraction has an x. This second fraction has an x plus 5. That means I'm missing an x in my second fraction, and I'm missing an x plus 5 in my first fraction. Does that make sense? We need both of these factors here. It is not enough, and I'm not allowed to just simply add a 5 to the denominator and add a 5 to the numerator of my first fraction. It doesn't work that way. Remember when we talked about introducing a factor? When we introduce a factor, it's through the process of multiplication. We want to multiply the denominator by a quantity so that it becomes identical to the other fraction, right? That's what we're looking for. We want to make them the same, and the only way to do that is by introducing a factor, by multiplying by the missing factor, not just adding a number in there. Doesn't work mathematically. Which means our LCD in this case is going to be x times x plus 5. As a reminder, we would be multiplying our numerator by x, and we'd be multiplying our numerator in the first fraction by x plus 5. I know there's a lot of writing going on all over the place, but hopefully this is making a lot of sense. Okay? For part L, same thing. Notice your first denominator is x minus 5. Your second denominator is x plus 5. So I'm pretty sure that you're shouting out exactly what that answer is, and you recognize that your LCD is going to be a combination of the two. So your first fraction needs an x plus 5, and your second fraction needs an x minus 5, so that they have the same denominator. So LCD is equal to x plus 5, and then of course x minus 5. I would like for you to take home parts M and N, and I want you to think about factoring the denominators. Of course, 2n plus 9, we can write that over a 1. I want you to consider factoring the denominators and then making them the same. So think about what you need to introduce so that the denominators are identical. Okay, so try these at home. I want you to try M and N at home. Okay? Beautiful. Let's turn the page. Okay. We are now ready to actually add or subtract rational expressions that do not have common denominators. We're finally ready for this. So we have our rules here. You can definitely look through those at any point that you would like. You have access to these notes at home. And also, if you're watching the video, you can definitely pause and just kind of read through those rules. But because we have this momentum of understanding how to introduce that missing factor, let's keep going with this. So for part A, I have the first denominator of x and my second denominator is y. In order to make them the same, I have to introduce a y for my first fraction, and I have to introduce an x for my second fraction. That way, my common denominator is xy. This leaves me with y times 1, which is y, over xy, plus 10 times x, which is 10x, over xy. You're probably wondering why I switched the order of the terms. Remember that every product is commutative. Y times x is the same as x times y. And typically, we like to write our factors in alphabetical order if possible. So xy is more of like that math etiquette piece. So you want to write that in alphabetical order. Now we want to finish this by adding our fractions. They have the same denominator, so I'm going to go ahead and write the denominator xy, and then I'm simply going to add across my numerators. So this gives me y plus 10x. I am actually totally accepting of this answer. There's nothing wrong with this answer. If you would like, I'm going to write or. You could write your answer as 10x plus y all over xy if you wanted to write it in alphabetical order. Okay, completely up to you. Either answer works in this case. That's what it looks like to add or subtract rational expressions that do not start with a common denominator. Check out part B. We have 6xy to the third in our first denominator, and then we have 9x to the fourth y. At this point of the video, because we've had so much practice finding common denominators, when you're watching this at home, you may want to pause right here. So that way you can give B a shot and kind of play around with trying to figure out what that common denominator is. Figure out what those factors are, multiply, and then combine the two fractions and see what happens. Okay? But besides that, let's keep going together. So I have a 6 and I have a 9. And I start to think, well, the multiples of 9 are 9, 18. The multiples of 6 are 6, 12, 18. So right away, I know that I want both of the denominators to become 18. So immediately I say I need to multiply at least by a 3. for my first fraction. For my second fraction, I need to multiply by a 2 so far. Next, I have x to the first power in my first denominator, but x to the fourth. So in order to make them match, I need to introduce an x to the third. I'm going to do the same thing to the numerator, of course. Lastly, I have y to the third in my first denominator, but a single y in my second. So that means I need 2 more y's on this side. So I'm going to introduce 2 more y's here. So let's check this out. 3x to the third times 7 is 21x to the third. My denominator is 18, x to the fourth, y to the third. 18, x to the fourth, y to the third. Then we have our plus. My second fraction is 4y to the second power. All over, let's check this out, 18, x to the fourth, y to the third. Perfection. We know that we're on the right track when we introduce a missing factor and find that we have identical denominators. This is looking great. The last thing we want to do is we want to combine the two fractions. We want to actually add them. So we're going to keep our denominator, which is 18x to the fourth, y to the third, and I'm going to add across my numerators. 21x to the third plus 4y squared. I cannot combine these two terms. I also don't have a GCF. So I'm actually done with this particular problem. Okay? Let's check out part C. Notice my denominators for part C. I have x minus 5, but then I have 5 minus x. We want to fix this fraction, this denominator specifically. So we have negative x plus 5, which is the same as negative 1 times x minus 5, right? Because I'm factoring out, that leading negative. The next thing I want you to consider is what we learned about the negative sign of a fraction. So I can actually take this positive and multiply it by this negative, so that my expression becomes 3 over x minus 5 minus x plus 2 over x minus 5. Luckily, by manipulating that denominator and by cleaning up the signs that separate the two fractions, I now have fractions with the same common denominator. So when I go through the process of subtracting my fractions, keep in mind the very first thing is I must distribute that negative sign. So this gives me 3 minus x minus 2 all over x minus 5. Every single time you want to combine like terms whenever possible. So that leaves me with negative x plus 1 over x minus 5. The very last thing we'll want to do is we want to factor if possible. Because my numerator has a leading negative, I'm then going to factor that negative 1 out. And voila, I am finished with my problem. Make sure that your final answer is completely factored. Okay? Let's look at some more examples. We're going to get a little bit more complicated now. Okay? It's going to take a little bit more of work room in order to make this happen. Take a look at part D. 2 over x plus 5. Here's my expression that sticks together, minus 3 over x. Immediately, I recognize that I'm missing an x from my first fraction, right? And I'm missing an x plus 5 in my second fraction. So let's rewrite what this looks like. It's always going to be helpful if we see this. So we have 2x over x times x plus 5 minus 3 times x plus 5 over x times x plus 5. So far, this is looking great. I notice that my denominators are the same, and I can take a step forward. I can do a couple things. I can look at this as a -3 and distribute that throughout my parentheses, or I can do two steps. I can start by distributing the 3 and then distributing the negative. So it's completely up to you how you would like to work through this problem. For the sake of breaking this down step by step, I'm going to start by only distributing the 3. So that leaves me with 2x over x times x plus 5 minus 3x plus 15 over x times x plus 5. Cool. I distributed the 3 so that I can drop parentheses. I'm still subtracting fractions, so I now want to make sure I distribute the negative throughout. You see how we're working through this piece by piece. We want to make sure that we don't lose any signs as we do this. So this means we get, and actually, you know what? I'm going to combine my two fractions. So let me go ahead and rewrite this. I'd rather write it so that it looks nice and clean. I'm going to rewrite the entire numerator over the same denominator. This gives me 2x minus 3x minus 15. So minus 3x minus 15. Combine like terms. Negative x minus 15 over x times x plus 5. And then last up, our leading term is negative for our numerator, so we're going to factor out the -1. And notice that we do not have any common factors that we can divide out, so we are officially done. Excellent. Notice for part E, we have our denominators x plus 1 and then x squared minus 1. Our first step is always to factor the denominators if possible. Our denominator here is x squared minus 1, which represents the difference of two perfect squares. When I go ahead and rewrite this, I have x plus 3 over x plus 1 minus 9x plus 5 over, and then x squared minus 1 factors into x plus 1 times x minus 1. Same thing, we need to have a common denominator, so we think about what's missing in our first fraction, because they both have the x minus 1, but this one's missing that x minus 1. So let's introduce x minus 1, numerator and denominator. Beautiful. The next thing I'm going to do is I'm actually going to distribute these two. Because remember, we must distribute to drop parentheses so that I can combine all of my terms. I also want you to consider we're subtracting the second fraction, so no matter what happens, we're going to be distributing that negative throughout the second set of parentheses, throughout my second fraction. So let's do the math here. We get x squared plus 3x minus 1x minus 3. Let's keep it going. Minus 9x minus 5. So what I've done is I've opened up the entire numerator. I distributed the two factors that were in our first fraction in the numerator, and then I distributed the negative throughout the numerator of the second fraction so that everything was open up and nothing is in parentheses. My denominator is x minus 1 times x plus 1. I will tell you, you will always leave your denominator factored. Notice that every single time we do this, we're never redistributing the denominator. It stays factored. Okay, our logical next step is to clean up my numerator. This is a mess. So we have x squared. I have 3x minus 1x, which is 2x, minus 9x, which is a negative 7x. I then have negative 3 minus 5, which is negative 8. And all of this over x minus 1 times x plus 1. I told you there's a lot of work involved in this, but it's really not bad as long as you take this step by step. Be very deliberate in every step that you take and just move through this slowly. There's no need to speed through it. The next thing I'm going to do is I'm going to try to factor my numerator. I have a trinomial. My leading coefficient is equal to 1, so I'm going to go ahead and use trial and error, if possible. I want factors of negative 8 that combine to give us negative 7. Well, that's got to be negative 8 times 1. Negative 8 times 1 gives us negative 8. Negative 8 plus 1 gives us negative 7. So we'll write our factored form as x minus 8 and x plus 1. We'll rewrite the denominator directly underneath. And then notice that once everything is completely factored, we do have common factors that we can divide out. And that happens to be the x plus 1s. So my final answer for this problem is going to be x minus 8 over x minus 1. Beautiful. Again, at this point, you may want to pause the video and try part F on your own before we look at it together. Make sure that you're factoring the denominator, find out the pieces that are missing and introduce those, and then multiply the numerator so that you could drop all parentheses, combine them into one fraction, and then of course factor and reduce. There's so much going on here, but I'm hoping that you're seeing that it actually has a very logical flow. It's kind of the only thing that makes sense. You have to take into account they have different denominators. Make them the same first. Once they're a complete fraction, one fraction, that's when you try to break it down again, right? So that's the process you really want to go through, okay? Let's scope it out. In our first fraction, we have 4 over x squared minus 4x. So I'm going to rewrite that. We have 4 over x squared minus 4x, I notice it has a GCF. So I'm going to factor out x. That leaves me with x minus 4. Minus, then we have x over, and then 4x minus 16 also has a GCF. It's 4. So I'm left with 4 times x minus 4. The great thing about this problem is that they both have the x minus 4 already. This one has an x and this one has a 4. So let's give the 4 here to the first fraction, and let's give the x here to the second fraction. Let's see what we have. 16 minus, so we have 16 minus x squared all over my common denominator, which is 4x times x minus 4. My numerator is the difference of two squares. We know it's not in descending order. Don't panic. I don't want you to worry about that whatsoever. You can rewrite this in descending order and then factor, but I'm actually just going to factor it as is. So we have 4 plus x times 4 minus x. Because 16 comes before the x squared, we really want to be careful with how we factor this. So 4 plus x times 4 minus x directly gives us the 16 minus x squared. You want to make sure that they're identical, especially if you don't manipulate it. Okay, you leave it as is. All over 4x times x minus 4. One thing we learned earlier today is that when we have these quote-unquote distant cousins, right? I don't know why we call that. We just always have, for whatever reason, when I was learning this in school. When you have these distant cousins, 4 minus x and x minus 4, we learned earlier that these are going to divide out, leaving you with a negative 1, which is super cool. We learned earlier why that is, so make sure you go back to that piece of information in our notes or in our video to verify why that was again, that they divided into a negative 1. Check it out and you will see exactly why that is. So let's go ahead and write our final answer. We have -1 times 4 plus x all over 4x. And that is as far as you can go. Consider that you would need an exact 4 plus x or x plus 4 in the denominator in order to cancel it, but you don't have an exact match, so you can't actually go forward from there. All right. Excellent, excellent work. As always, if you have any questions that you want to throw in the chat while you're here, you totally can. But we have one more that we may as well look at and just have some fun with. Part G is definitely a lot more busy. It's not in the sense that it's too hard to do. It's just a lot busier. There's a lot more going on here. So I'm actually going to demonstrate G for you just so that you are confident if you ever saw problems like this in the future, which you can. You can potentially see on like a comprehension check or a test. So even though G is going to feel a little bit more intense, we can still manage this just as well as any of the rest of them. Okay, let's take a look. I'll do this with you. And again, if you're at home watching this later on, pause it. Give it a shot first and let's see what happens when we compare work. So we have x plus 8 over x squared minus 2x minus 8 plus x plus 1 over 2x squared plus 7x plus 6. Whoa. Okay. First things first, you're going to want to factor both of these denominators. Okay. So we have x plus 8. We have x squared minus 2x minus 8, so I'm going to factor using trial and error, right? I need to find factors of -8 that combine to give me a -2. That's going to be -4 and +2. That's what's going to give me -8 when I multiply them, and when I add them, I'll get a -2. So right off the bat, I'm going to write x minus 4, x plus 2. So there's my first fraction. That's my factored form. For my second fraction, I have x plus 1 over, and now I'm going to use AC grouping to factor this particular polynomial. Since it's a trinomial, my leading coefficient is bigger than 1. When you use AC grouping at home to factor this polynomial, you're going to notice that you'll have 2x plus 3 and then x plus 2. Let's double check. 2x squared plus 4x plus 3x is 7x plus 6. That looks great. Now, time to introduce the missing factor. Okay. I have an x minus 4 on the left, and I don't have that on the right, so I need to introduce that. On the right-hand side, I have a 2x plus 3, but I don't have it on the left, so I need to introduce that over here. So we need to introduce the 2x plus 3 and the 2x plus 3. I'll put it in front. Okay, so we introduce the 2x plus 3's on the left, and we introduce the x minus 4's on the right, right? First fraction versus second fraction. Okay. Naturally, I want to be able to combine these two fractions, but I have a bunch of parentheses in my numerators, so I need to open these up. We already know how to open these up. We do that by actually multiplying. So we're going to distribute term by term. Same thing here as well. So let's start with this first fraction. And by the way, because all I'm doing is distributing and then adding the second one, I'm just going to list the whole thing as one massive numerator. Okay, let's see if it all fits. X times 2x is 2x squared. X times 3 is 3x. 8 times 2x is 16x. 8 times 3 is 24. Plus x times x is x squared. X times -4 is -4x. 1 times x is 1x. 1 times -4 is -4. Whew! Okay, It was a lot, but it wasn't unmanageable. It's not something that we are unfamiliar with. We're totally familiar with the product of binomials. That's no big deal. We've done it a million times. My denominator is 2x plus 3, x minus 4, and x plus 2. Yes, it's a lot. But no one's asking you to multiply these three. You're going to leave them in factored form, so you can kind of breathe easy when you think about that. The next thing you're going to want to do is you want to clean up your numerator. Let's combine like terms and see what happens. 2x squared plus x squared is 3x squared. 3x plus 16x, that's 19x. Minus 4x is 16x plus 1x. Did I do this right? Let's see. 3x and 16x, it's 19x. Minus 4x, let's do math correctly, it's 15x. You see how I caught myself? 15x plus 1x is 16x. Hey, nobody's perfect, right? Next, we have a positive 24 minus 4, so plus 20. Okay, so far so good. This is becoming pretty clear where we want to go from here. So let's go ahead and write our LCD. Okay. Because we have a trinomial in my numerator, where my leading coefficient is greater than 1, I'm going to attempt trial and error. Luckily for me, AC grouping. When I use AC grouping, I find that my factored form is 3x plus 10 times x plus 2. We should always double check, by the way. 3x squared, 6x plus 10x, that's 16x, plus 20. That looks great. Let's go ahead and write out my denominator and then see what happens. I can now divide out my common factors. My common factor in this case is x plus 2, so let's divide that out. There are no other common factors, so my final answer is 3x plus 10 all over 2x plus 3 times x minus 4. Not bad. Even though this seemed like it could potentially be a very problematic expression or example, we found that it was actually much more manageable than we probably expected. Sure, the denominator is huge, but it's no big deal. You're not being asked to multiply the product of these, you're not being asked to do the product of these three binomials. You have to leave them completely factored. You just have to introduce the missing factor, distribute to drop parentheses, combine them, factor, and then divide to have your final result. Lots of moving parts, I know, but it does get much easier, I promise. Okay? At this point, we are ready to move into something called complex fractions. When you think of complex fractions, we can essentially do this in two ways. The first way is we can look at this complex fraction as an expression in the numerator that we want to simplify, an expression in the denominator that we want to simplify, and then we have fraction divided by fraction, which means we are going to keep the first fraction and multiply by the reciprocal of the second, right? We use the rules for dividing fractions. That's no big deal. And actually, we can always use that approach. Sometimes, though, you may want to cancel the fractions that are in the complex fraction. I know, I'm saying weird things. Essentially, what that means is you would actually end up finding the LCD of all terms in your complex fraction, and you would multiply every term by that LCD so that you would cancel fractions. And then what ends up happening is it simplifies immediately to one fraction. And then, of course, you clean it up and see what happens. Which is better? They're both equally as great. It really just depends on the problem that you've been presented with, and it also depends on your own personal style. There are some cases where, you know, one method would lend itself better than the other method, but it's all equally, it all works, so to speak. But you will want to master both techniques because that will allow you to play around with what you should use when, and of course, integrating your own personal style into that. Okay? So I don't want you to feel overwhelmed at all. Just consider that we're going to start off nice and easy where we treat them separately, and then we're going to get fancy with it. Okay? Let's check it out. Complex fractions. So a complex fraction is a fraction that has a fraction in its numerator, denominator, or both. Yes, I've been saying fraction and factor a million times, and that's going to continue, so I'm sorry. Method number 1, change to a multiplication problem, right? So essentially, what we want to do is what I talked about. We want to write the numerator and the denominator as a single fraction each. So keep in mind that this represents the numerator of the complex fraction, and this part represents the denominator, let's see if I could squeeze that in, of the complex fraction. So we're going to treat them separately. We're going to treat them like they're two different problems. Here's what I mean. So we have 7 over 3 plus 1 over 4. And you're like, okay, my LCD in this case is 12. So I'm going to multiply by 4 here. I'm going to multiply by 3 here. This gives me 28, and this is 3. So 28 plus 3, that's going to give me 31. So I have 31 over 12. There's my numerator of my complex fraction, right? Would you agree with that? Then I'm going to look at the denominator of the complex fraction. So it's 5 over 2 plus 1. But 1 is, we can always write over 1. Every whole number we can place over a 1. I still need a common denominator. My common denominator in this case is 2. So I just have to multiply my second fraction by 2. So we have 5 plus 2, which is 7, over 2. Okay. And voila. I have converted each expression, numerator and denominator, into single fractions. Now that they're single fractions, I can keep the first fraction and multiply by the reciprocal of the second. You see? Now I'm able to simplify wherever possible. So 2 goes into itself once and into 12 6 times. I notice that nothing else can reduce, so I'm left with 31 over 42. And there's your final answer. So this essentially represents method number 1, that we would treat them separately, and then I would keep, switch, flip, multiply by the reciprocal of the second fraction. Okay? Let's check it out with more complicated problems. Part A is really nice because it's a single fraction divided by a single fraction. So we're going to keep the first fraction and multiply by the reciprocal of the second fraction. In this case, it turns out that nothing reduces. So we simply multiply from left to right. 15a times 5 is going to give us 75a. And then b to the second times b to the third, keep the base, add the powers. B to the fifth, and we're done. Check out part B. We have a plus a over 2. Again, treat them like two separate problems. So we're going to look at just the numerator of the complex fraction, and then we're going to look at just the denominator of the complex fraction. Okay. A over 1 plus a over 2. My LCD is going to be 2. So let's introduce that factor to the first fraction. This gives me 2a plus a, which is 3a. And my common denominator is 2. For my denominator of the complex fraction, I have 2 over a plus 1 over 2a. The missing factor is 2. So I'm going to multiply the first fraction by 2. So this gives me 4 plus 1, which is 5. And my denominator is 2a. Now that I have fraction divided by fraction, I am going to keep the first fraction and multiply by the reciprocal of the second fraction. When we multiply fractions, we always look to reduce first. Notice that the 2's can divide out, so 2 into itself once and into itself once, and that's it. Nothing else reduces. The 3 and the 5 cannot be reduced, and these a's are both in the numerator, so you can't do anything with those, except for we can now multiply. 3a times a is 3a squared, and 1 times 5 is 5. And there's your final answer, 3a squared over 5. Okay, take a look at part C for one moment. Don't freak out. One of the things, you're probably looking at this and you're like, what? Recall the rules for exponents. We had a negative exponent rule. So whenever we had a base to a negative power, we would always write it as the reciprocal of that number, right? So for instance, if I had, 3 to the negative 1, I would write that as 1 over 3 to the positive 1. So you'd write it as the reciprocal with a positive power instead. Similarly, if that variable or that base with a negative exponent was in the denominator, we would then write the reciprocal so it moves up top to the numerator and again has a positive power. So the act of moving from numerator to denominator essentially changes that power from negative to positive. So we're just applying that rule here. What I'll do is I'll put a little note in these guided notes so that it serves as a refresher of that negative exponent rule. I think that's going to be super helpful. So let's take a look. Recall that if we had, for instance, x to the negative 4, we would rewrite that as 1 over x to the positive 4. Similarly, if we had 1 over m to the negative 3, this entire expression would move up to the numerator and it would have a positive power, so m to the positive 3. Okay, that's essentially all that's happening. We are going to apply the rules for negative exponents to this particular problem by rewriting it. So it just looks a little scary right now, but it really is not bad at all, and I promise that it's not. So a to the negative 2, just to kind of make some notes up here, a to the negative 2 is the same as 1 over a squared. A to the negative 1, b to the negative 1, that's the same term, right? That becomes 1 over a to the first, b to the first. You see, it's really not that bad at all. We have 2b to the negative 2. Notice that only the b is being raised to the negative power, not the 2. You would need 2b to be in parentheses, then raised to the negative 2 if that power were to be applied to that base 2. But it's not. It's only being applied to base b. So this becomes 2 over b to the second power. And then we have 2a to the negative 2. Again, same idea. Only the a is being raised to the negative 2 power, so that's the only base that's going to move. So you're left with 2 over a squared. Now that I have dissected each of these terms, I can rewrite this problem so that it becomes much more manageable. So in my numerator, I have 1 over a squared plus 1 over a to the first, b to the first, all over 2 over b squared minus 2 over a squared. Cool. Let's start with the top. If I have 1 over a squared and I have 1 over a to the first b to the first, I'm going to look at the a's initially and say, well, I have 2 a's here and I only have 1 here, so I need to introduce 1 more. And then I notice that I have a b in my second fraction, but I don't have a b here, so I need to introduce a b. So that leaves me with b plus a all over a squared b, a squared b. Perfect. Let's rewrite the denominator, so 2 over b squared minus 2 over a squared. Well, my first term has a b squared, but is missing the a squared, so let's go ahead and introduce that. But my first fraction had a b squared, but my second fraction doesn't, so I'm going to introduce the b squared, that missing factor. So now I have 2a squared minus 2b squared all over a squared b squared. And here's my complex fraction. We're going to keep the first fraction, b plus a over a squared b, and we're going to multiply by the reciprocal of the second fraction, a squared b squared over 2a squared minus 2b squared. Before we reduce or cancel or anything, we have to factor completely. I want you to notice that b plus a is set. We're good. A squared b, we're good. A squared b squared, we're good. 2a squared minus 2b squared, no, we can factor. The first step of factoring is GCF, so I'm going to take out the 2 from both terms. The next thing I'm going to notice is that, and I'm going to rewrite it so that it's easy to see, excuse me. Let's rewrite this. We have b plus a over a squared b times a squared b squared all over. Now, our GCF is 2. And then when we want to factor a squared minus b squared, we recognize this is a difference of 2 squares. So it becomes a plus b times a minus b. Now that everything is factored, we can start to cancel. Notice b plus a and a plus b are identical. Even though the order flipped, it's exactly the same expression. 1 plus 2 is the same as 2 plus 1. A plus b, it has to be the same as b plus a. It's a commutative property. So we're going to divide out this common factor. Next thing I notice is that I have an a squared and an a squared, numerator for denominator. So we're going to divide these out. The last thing I notice is I have a b to the first power in my denominator and a b to the second power in the numerator. So I'm going to subtract the powers and leave it where it's heaviest. So I'm going to take one factor of b away here and one factor of b away here. That leaves me with a single factor of b. So my final answer is going to be b to the first all over 2 times a minus b. And voila, you're done. So that strategy is really, really great in terms of saying, you know, I want to treat them as 2 separate problems. I want to take care of the numerator of the complex fraction. I want to take care of the denominator of the complex fraction. And then I'm just going to keep switch flip, right? Because you're familiar with the rules for dividing fractions and you feel comfortable with that. What I'm about to show you in this second technique, and this is the last thing we're going to do for today, with this second technique, it can actually be really, really, really nice. Like super, super, super nice. I use this technique if I notice that it's going to end up being very straightforward to cancel fractions. Okay? Essentially, the trick here is find the LCD of all of the fractions in this complex fraction. So you literally look at everything at the same time And then you say, okay, I know what the LCD is, so I'm going to multiply every single fraction in my complex fraction so that I can cancel fractions. Oh my God, it's so weird to describe it. Let me just show you. It's a really great technique. And like I said, you really should get comfortable with both of them so you can kind of choose, which one to use depending on the type of problem that you're presented with. Okay, but either way, it's going to work. It's just one might take more effort than the other. All right, let's check it out. Hopefully this is not too overwhelming. And again, as always, I recognize that this is such a fast-paced course. So just kind of take a break, take a breather, come back to the video, rewatch it, and make sure that you're taking your time and you're allowing yourself the time to digest it, okay? So don't feel like if you don't get it instantly that something's wrong with you. That's definitely not the case. These things take time. So be willing to sit in that discomfort because you will grow comfortable. But you got to get through that discomfort first. Let's check it out. Okay. We are going to use a technique of clearing fractions. So we're first going to find the LCD of all fractions, and then we're going to multiply every single term in that complex fraction by the same quantity. Check it out. Let's take a look at this example here. I have a 3, a 4, a 2, and I even have a 1 here in my denominators, right? Looking at all of these denominators, I can safely say that my LCD is going to be a 12. Right? 3 can become a 12, 4 can become a 12, 2 can become a 12, and then obviously 1 can become a 12. Now we're not going to do what we did last time. We are not going to multiply by the missing factor. We are going to take that LCD, which is 12, and we're going to multiply every term in this fraction by 12. Check out how cool this is. If we multiply every term by 12, look at what happens. 3 goes into 12 4 times. 4 times 7 is 28. There's no fraction anymore here because the 3 went into the 12. So it canceled out my first fraction. It eliminated it. Plus 4 goes into 12 3 times. 1 times 3 is 3. Interesting. 12 times 5 over 2. 2 goes into 12 6 times. 6 times 5 is 30. Plus, obviously 1 doesn't go into 12. 1 times 12 is simply 12. Now check this out. 28 plus 3, that gives us 31. 30 plus 12, that gives us 42. This is definitely an interesting perspective because we just were able to do the same thing, but by treating our fractions essentially differently, right? Let me show you the previous problem. So here we canceled our fractions. But in our previous attempt, we treated the numerator of the complex fraction and the denominator separately. We had a fraction for each, and then we did the whole keep, switch, flip thing, right? You multiply by the reciprocal of the second fraction. But look at how quickly I got to my answer using my second technique. Not to say that this is going to be the superior technique every single time, clearing fractions, because definitely sometimes you're going to want to use our first strategy of treating them as separate problems. But, I mean, sometimes it makes life a heck of a lot easier. Kind of cool, right? Let's keep going. Let's do it again. We have 3 plus 1 over x all over 1 over x squared plus 3 over x. Okay, cool. I'm going to look at all of my fractions here. I'm going to write this 3 over 1 because, I like to see them all as fractions. If I look at all 4 denominators, it's clear to me that my LCD has to be x squared, right? It has to be x squared. Remember, we're looking for a common multiple. And we can easily make each of these denominators x squared if we just introduced another x and if we introduce an x squared here, right? But remember, we're canceling fractions. So take each term, place it in parentheses, and multiply each term by x squared. And let's see what happens. X squared times 3 is 3x squared. Can't x go into x squared? It can. If we divide out a single x, we're going to divide out a single x. So we're left with plus a single x. In our denominator, notice x squared and x squared, they will divide out, leaving us with a 1. Plus, notice x can go into itself once and into x squared once as well. And that leaves us with 3 times x, which is 3x. I'm going to take this a step further by factoring the numerator. I have a GCF of x, so let's factor that out. Now that I have my expression completely factored, I notice that I have a common factor that I can divide out. 3x plus 1 and 1 plus 3x, these are the exact same expression. They divide out, leaving you with an answer of x, and you're done. This process can be so much nicer than our previous strategy. Again, not to say that it's any less valuable, okay? Just kind of play around with that and decide which one you like better, and then of course when you feel like you should use one versus the other. Let's do this one. We have 2a over b plus a to the negative 1, that's the same as 1 over a to the first power, all over b over a plus a to the negative 1 is 1 over a to the first power. Good. Look at all 4 fractions. We see that our LCD is a times b. It's got to be a combination of the two, right? Think back to everything we've done so far in this session. So since our LCD is a times b, let's go ahead and multiply every term and see what happens. Da-da-da. Every term, we have 4 terms, a times b, a times b, a times b, and again. Let's divide out. So b's divide out, so you're left with a times 2a, which is 2a squared. A divides into a, which leaves us with plus 1b. In my denominator, my a's are going to cancel. That leaves me with b squared plus, and then of course my a's are going to cancel, and that leaves me with b. I'm going to factor where possible, so I have 2a squared plus b. There's no GCF, so I have to leave it as is. But in my denominator, I can factor out a b, and I'm left with b plus 1. Unfortunately, there is nothing that reduces. Remember, I can't just cancel this b out because in my in my numerator, 2a squared plus b is one whole quantity, right? Meaning they're connected to each other by addition. It's not like it's 2a squared times b where then I can divide out that b. So we want to be really, really careful that we don't cancel out any terms. We only cancel out factors. So this is actually complete. At this point of the video, again, I would like you to pause and give part C a shot on your own. Try this out. Make sure that you're understanding the process through this, multiplying by the LCD to clear fractions, and then to combine and factor and then reduce if possible. So you really want to be careful following that flow. But we are going to end this session with that class, or this particular problem, that class. I can't even talk. We're going to end with this particular problem, okay? Let's take a look and see how it goes. So hopefully you, if you're watching synchronously right now, that you've already started to really move through this problem. And then what I'll reveal to you is the work that you should have done. Let's take a look. 2 over x minus 1 plus 1 over x over 6 over 1 plus 4 over x minus 1. I notice that my LCD in this case is going to be x times x minus 1. Think of this x minus 1 as being in parentheses. It's an expression, right? X minus 1. So we're going to keep that in parentheses, which means we're missing that x from the first fraction and the x minus 1 from the second, etc., etc. We are using the strategy of multiplying by the LCD. So take each fraction and go ahead and write them in parentheses so that it's a reminder to us to multiply by the LCD. Each term gets multiplied by the LCD. Good. For our first fraction, our x minus 1s are going to cancel. So I'm left with 2 times x, which is simply 2x. For my second fraction, my x's are going to cancel. So that leaves me with 1 times x minus 1 plus 1 times x minus 1. We're going to fix that in just a bit. In my denominator, I have nothing that cancels, so I have x times x minus 1 times 6, which is the same as 6x times x minus 1. Then we have plus. Then notice my x minus 1s are going to cancel, and that leaves me with a positive 4x. Cool. I need to distribute to drop parentheses. We're going to do that in both cases. 2x plus x minus 1 all over 6x squared minus 6x plus 4x. All we have to do now is combine like terms. 2x plus x is 3x, so I have 3x minus 1. Then I have 6x squared minus 6x plus 4x is minus 2x. I cannot factor my numerator, but I can factor my denominator. So I have 3x minus 1 over, let's take out my GCF. My GCF is 2x. That leaves me with 3x minus 1. And look at how cool this is. I have a common factor of 3x minus 1, so I'm going to divide these out. And I'm left with, now be careful. The 2x is in the denominator. It doesn't just all of a sudden jump to the numerator. It doesn't work that way. Why would it, right? Since when have we been allowed to just take a value in a denominator and throw it in a numerator? Never. We are never just allowed to move things around just because. You have to have like a negative exponent, or you have to perform some sort of operation. So seeing as we're just writing what we have left over, we will write down that we have a 2x in the denominator. And then, of course, because 3x minus 1 divided out 3x minus 1, that left us with a 1 for the numerator. So our final answer is 1 over 2x. Excellent work. Thank you so much for hanging in there. I know it's a lot of content, but with practice, this is going to be really, really great. Also keep in mind, a lot of this is pretty repetitive, right? It's a lot of the same stuff again and again and again. Make sure that no matter what, you factor before you cancel, okay? Never cancel terms, only cancel out or divide out factors. That's what you're looking to do. If you can keep that in the forefront of your mind, that's going to make this a heck of a lot easier. And on that note, I will see you all on Monday. Please look for an email from me within the next few minutes with a recap of the week and instructions to be prepared for next week. Bye, everyone.